Hey guys, I hope you're doing well. In this video, we are looking at a signal flow graph. What a signal flow graph is, how do we solve it, how do we find the transfer function out of it. The name itself suggests flow. So this is how this graph is, and any system that is linear can be represented by using a signal flow graph. And when you are given a signal flow graph, you can easily find out the transfer function from it. And to do that, there are actually two ways. I call the first one the blunt way because it is pretty tedious and time taking, and the second is Mason's gain formula, which is easy and the smart way to do things. When you're solving the signal flow graph in the normal way, there are some guidelines, but before that, let's look at some terminology. So the first thing that we have is a node and the next is a branch. So nodes are where signal comes in, signals go out, and branch is where the signal actually passes through, right? And every time the signal passes through a branch, it gains something, and this is called transmittance. And the next thing is, if at any node there are only outputs, the node there are only outputs, there are no inputs, such a node is called source node, like the sun, it's only giving output. There is one more node where there are only inputs coming in. So this kind of node is called the sink, like a black hole. For guidelines, first we will look at two nodes, say N1 and N2, and these nodes are in series, okay? And the transmittance or the gain that is happening here is G. The signals at nodes N1 and N2 are S1 and S2. So what is the signal at N2, right? So in this case, you will just multiply the signal at the input with the gain of the branch. So basically at N2, you will have S1G. Similarly, when there are say two nodes coming into one node, you just have to multiply N1 node signal, which is S1G1 and S2G2, and then add them up to get the signal at the node N3. The same thing you can do for branches. Say there are two branches in series, you can just take a product of the transmittances. So you can remove the node N2 completely, and the transmittance of this branch can be represented as G1, G2. And when the branches are in parallel, you do the exact same thing, you just have to add them up. By now you must have guessed it. The only challenge comes in when there is a feedback loop. It gets a little bit tricky. Let's say there are three nodes and then we have a feedback loop between N3 and N2, which is giving a signal H. Now, how do I remove the node N2 and just put in the transmittance between N1 and N3, right? So at N2, you're getting two signals, which is N1G1 plus you are also getting N3H, right? So at N2, you have N1G1 plus N3H. All right. At N3, the signal that you're getting is N2G2. That's all you're getting, right? So at N3, let me substitute the value of N2. So I have N3 is N1G1 plus N3H into G2, which is N1G1G2 plus this. So now I just need to put it in such a way that, N3, right? If I multiply this transmittance with N1, then I'll get the signal at N3. So that value I need, which is basically N3 by N1, right? So here N3 is N1 into G1, G2 by 1 minus H G2. So N1 is you multiply. So basically the transmittance is G1, G2 by 1 minus H G2. So guys, now let us look at Mason's gain formula. So until now, we saw the different guidelines that are supposed to be used in reducing a signal flow graph and getting its transfer function. But as you have noticed, it's really tough and it's very, very, very tedious. So that is why we use the Mason's gain formula. So this is gonna help us find out the transfer function very easily. So I'm going to represent the transfer function with t, and this is going to be C of S by R of S. This is the output, this is the input, I don't have to tell this to you guys, you know this, right? The transfer function t is represented by 1 by delta summation of pk and delta k. So now I'm definitely going to help you with a couple of examples, but even before I do that, I have to explain the formula itself, because each thing signifies something, each variable. So that is what we'll look at. First things first, what is k? K is the number of forward paths. So what is a forward path? So let me just take this signal flow graph. Let's give it one feedback, two feedback, this is forward. So the straight thing is all forward. Okay, this is going forward. Okay, so now this is our signal flow graph, a very basic one I've taken just to show you an example. So the number of forward paths here is 2. You know why? The first forward path is a straight line. Okay, the second one is this, right? So it can go like this and then this way, or it can go follow the straight path. For example, there was one more here. Then there will be 3 forward paths. Or there is one more here, which is, going like this. Then there will be 4 forward paths. So k is basically the number of forward paths. So now you know what the forward path is, right? Now, what is pk? Pk is the forward path gain for whichever path you are finding out. For example, P1, let us say the Pk is the kth forward path. Let's say kth, okay? So for the first forward path, when you're finding out the gain, which is P1 value, the value will be the gain of this whole path. And for the second one, which is P2, it's gonna be the gain of this forward path. As simple as that. Finding out the value of pk is the easiest. Now comes finding out the value of delta and delta k. This is a little bit attention deserving. Okay. So first I'll tell you what delta is. Delta is 1 minus sum of all individual loop gains. So we did a minus. So this is going to be plus sum of gain products of all possible combinations of 2 non-touching loops. I'll come to this. This is why we are, having an explanation of the formula in the first place. So now we did a plus. So now minus sum of gain products of all possible combinations of 3 non-touching loops. Now we did a minus. So now we get a plus. So this is going to be sum of gain products of all possible combinations of 4 non-touching loops. Again minus, so on. 5 non-touching loops. But trust me, in your exams, if you come until 3 non-touching loops, that itself is more than enough. Most of the cases they'll stop with 2 non-touching loops. Okay, if it's 3 also, it's going to be a little bit lengthy for you to solve. So now what is the question here? What exactly is a non-touching loop? We have this signal flow graph, right? We have it here. So loops are basically those feedback paths. So just that there is this projection here, this is not a loop. Okay, here feedback is going by, it's in a loop, basically loop, forward path, loop. Forward path is going from input to output directly. Loop is coming back. So this is loop 1 and this is also loop 2. We have 2 loops here in this example. So first is sum of all individual loop gains. No. So what will loop 1 be? This is loop 1. If say this is G1 and this is H1, this gain will be G1 H1. As simple as that. And this is loop 2. Simple. We got that. So the second part is sum of gain products of all possible combinations of non-touching loops. So this loop here and this loop here, are they touching each other? No. right? So this will be a pair of non-touching loops. So sum of all gain products of all possible combinations of non-touching loops. So G1H1, this one will be G2H2. I'm just throwing examples. So what will this be? This is gonna be G1 H1 G2 H2. This is one product. We don't have a second pair of non-touching loops. For example, there was one more loop here which is L3. Now tell me, the first combination will be L1 L2 non-touching loops. Second combination will be L2 L3. Third combination will be L1 L3. In that case, the sum of gain products of all possible, this is the first gain products of L1 and L2, right? So for the second one, which is L2 L3, this will be G2H2 G3H3 plus the third combination of two non-touching loops, which is L1 L3, right? So G1H1 G3H3. So this is gonna be the second part of this. We have done that. So now three non-touching loops, which is L1, L2, L3. We do have, since we have done it like this, we do have three non-touching loops. So this is gonna be the sum of gain products of L1, L2, L3, which will be G1H1, G2H2, G3H3. In that way, for example, there was one more here, one more loop here, L4. Then L1, L4, L1, L3, L1, L2, L3, L2, L3, L4, all the possible combinations of 2, all the possible combinations of 3, 4, and so on. We won't really come to these things. Now, what if L3 and L4 are at the same node, okay? They are L3 is touching this node, L4 is also touching the same node. L3 and L4 will be a touching loop. You will not consider L3 and L4 when you are calculating any of these combinations. For example, L1 and L4 are still a pair of non-touching loops. L2 and L4 is a pair of non-touching. But L4 and L3 is not a pair of non-touching loops. So that is what a non-touching loop is. I hope you got a picture of that. Now we found out what delta is. Now what is delta K? Delta K, basically how many forward paths are there? You have to find out those many delta Ks. So delta 1, delta 2, delta 3, how many forward paths? So now we have 2. So delta 1 and 2. This is basically the delta. For that part of the graph. Say for example, for when I'm taking this straight forward path. This is the delta for that part of the graph which is not touching this forward path. For example, is there any part of this graph which is not touching this first forward path? The answer is no. Is there any loop? L1 is touching, L4 is touching, L3 is touching, L2 is touching, right? For this one, is there any loop? Is there any part of the graph for the second forward path? Is there any part that is not touching it? Actually, no, because L3 and... For example, let us say there is one feedback path here. This U that I'm drawing here. So this is not touching this second forward path, right? So the delta is basically the gain of this part of the graph. I mean, if the whole graph was, I know it's getting messy. So top left. So the whole graph is like this, okay? And there is a whole world here, all of this. In that case, to find out the delta K, you have to find out delta of this part of the graph, which is not touching this forward path. So this is what you need to keep in mind, and this is what Mason's gain formula is. I hope you just got a rough picture. So now let us say that we have one signal flow graph. We have the input R of S and we have the output C of S. How many nodes shall we give it? Let me write down the formula again for you. 1 by delta summation of pk delta k sigma goes to k. So first things first, pk, k. How many forward paths here? How many forward paths here? The straight line is one forward path, 1 to 8. And again, from this, we actually have to call this something. I'll call this G6. This is one forward path, which has G1, G2, G3, G4, G5. Forward path 1. What is forward path 2? It goes till here, then G6, and then here. So this is G6, G4, G5. So what is PK? PK is gain of the kth forward path. So P1 will be G1, G2, G3, G4, G5. What will P2 be? You guys can solve ahead of me and then check you're getting things right. So what will P2 be? P2 will be G6, G4, G5. So now we found out both P1 and P2. Now we have to find out delta K values. How many loops do we have here? We have 1 and 2. So first we find out delta. Let us find out the gains of these loops. So what are the two loops here? This is one loop, G2 minus H. I'll call this H1. And then there is one more, which is G2, G3 and minus H2. So what is the gain of the first one? This is the first one. This is the second one. What is the gain of this loop? You just multiply, right? What is the gain of this one? Second loop. Minus G2, G3, H2. So these are our individual loop gains. Now how do we find out delta? We need to find out what are the non-touching loops here. Here, how many loops are there? There are two loops. This is one loop. This is one more loop. So there are actually no non-touching loops here. So to put in our formula, what is delta? Delta is 1 minus sum of all individual loop gains. We found that there are two. All individual loop gains plus sum of products of pairs of all combinations of two non-touching loops. So here there are no combinations of non-touching loops, right? So delta is going to be 1 minus sum of these two. What is the sum of these two? Minus G2 H1 minus G2 G3 H2, which is basically 1 plus G2 H1 plus G2 G3 H2. So this is our delta value. So now we got the delta value. So what else are we supposed to do? Now we find out delta K's. Delta K, how many forward paths are here? This is one forward path, this is second forward path. Are there any loops which are not touching this forward path? No, right? So there is absolutely no loop that is touching this forward path, right? So your delta 1 value will be 1. All right. So what will your delta 2 value be? Is this going to be 1 again? No. So this is our forward path here. So is there any loop that is not touching this? Yes, right? So this loop is not touching our forward path. So you have to find out the delta for this. That's all. So G2 and minus H1. Delta 2. So what is delta? 1 minus sum of all individual loops, where there is only one loop. What else is there? So minus G2 H1 plus two non-touching loops. There is not that much of story running here. If there was one more and one more here, you would have to calculate so on and so on. But here there is only one loop, and even that also is a simple one, and there are no pairs of two non-touching, no cases of that. So it's simply 1 minus the first one, which is sum of all individual loop gains. So our delta 2 is 1 plus G2 H1. I think I gotta clear some space. So now our transfer function C of S by R of S is given by 1 by delta. What is delta value? This one. So 1 by 1 plus G2 H1 plus G2 G3 H2 into P1 delta 1 plus P2 delta 2. So what is P1? I'm gonna write this again. ठीक है. So 1 plus G2H1 plus G2G3H2 into what is P1? P1 is G1, G2, G3, G4 and G5. And delta 1 is 1 into 1 plus P2 is this G6, G4, G5 into what is delta 2? 1 plus G2H1. So what will that give you? G1, G2, G3, G4, G5 plus G4, G5, G6 plus G2, H1, G4, G5, G6 by 1 plus G2H1 plus G2, G3, H2. You can actually take G4, G5. Oh, sorry. Okay, G4, G5. Just G4, G5 because G6 is not part of this. So you can take out G4, G5 common and then mention it like this. G4, G5 into G1, G2, G3 plus G6 plus G2, H1, G6 by 1 plus whatever this is here. That is how we have found out the transfer function of this given signal flow graph. However, we got away without the complication of a non-touching loop. Now I want to add a non-touching loop to this. You know what? I should have kept that. This is all forward. Let me do one more forward. Call it G7. Okay. And now we need non-touching loops, right? So I'll give one feedback here, minus H1, and then I'll give one more feedback here, call it minus H2. Transfer function is given by 1 by delta summation of pk delta k, where k is the number of forward paths. So what are the forward paths here? There is the straight line and there is this. So the straight line, what is the gain of the straight line? Which is this one. This is gonna be G1, G2, G3, G4, G5, G6. So what is the gain of the second path? Second path gain is gonna be G7, G4, G5, G6. So I'm gonna write it as G4, G5, G6 and G7. So this is we found out P1 and P2, so P1 and P2 values. So now we got to find out delta value. And what is delta value? 1 minus sum of all individual loop gains plus sum of products of all possible combinations of two non-touching loops minus sum of products of gains of all possible combinations of three non-touching loops, right? So now for the first part of it, how many individual loops are there? This is one, right? This one, and then this is another. So we have two loops here. Let me draw them here. This is G4 minus H1. This is G2 minus H2, right? So what is the gain here? Minus G2 H2, and here it is minus G4 H1. So delta is equal to 1 minus sum of these, minus G2 H2 minus G4 H1 plus sum of the products of all the possible combinations of two non-touching pairs. So yes, these two loops are absolutely non-touching, right? So what do we write here? We take the summation of these two because we have only one pair here. So we are only going to have one product. So what will the product be? The product will be G2, H2, G4, H1 because both are negative. So the product has become positive. So this is going to be 1 plus G2, H2 plus G4H1 plus G2H2 G4H1. So this is the value of delta. So we have found out P1, P2, and we have found out delta, right? So now we need to find out the delta K's. Delta K is nothing but delta for the part of the graph, that is not touching the forward path. So first, this is the first forward path and this is the second one. So is there any part of the graph which is not touching this? This is touching, and this is touching. So your delta 1 will be 1. What is delta 2? So just like before, it's gonna be, because we have one loop here, right? Which is what? G2, this one. G2 minus H2. So this part of the graph is not touching our second forward path. So delta 2 is gonna be, you tell me. How do we find out delta? Delta is 1 minus sum of gains of all loops. Okay. There is only one loop. So this value is simply going to be 1 minus G2 H2. So this is going to be 1 plus G2 H2. This is your delta 2. If there was one more here, then you would have a non-touching pair. You do that and you solve it. Now that you have listened to all of this, you check such an example out. You just add one more path here and solve it for your practice. Nobody even needs to give you an example, right? So now we have all the values. We have delta 1, delta 2, delta, P1 and P2. Transfer function T is given by 1 by delta 1 by 1 plus G2H2 plus G4H1 plus G2H2 G4H1. What is this summation? P1 delta 1. What is P1? P1 is this. What is delta 1? Delta 1 is 1. So 1 into G1, G2, G3, G4, G5, G6 plus what is P2? P2 delta 2. P2 is G4, G5, G6, G7 into what is delta 2? 1 plus G2H2. Just simplify this and you will get the transfer function C of S by R of S. I'll still do it. G1, G2, G3, G4, G5, G6 plus G4, G5, G6, G7 plus G2H2, G4, G5, G6, G7 by 1 plus G2H2 plus G4H1 plus G2H2 G4H1. If you want, you can take out G4, G5, G6. G4, G5, G6 common here and then write it down. So yeah, this is how we find out the transfer function from a signal flow graph. We saw both the examples. We saw for non-touching loops and we saw for loops where there was contact, with contact and without contact. So hope you have found this informative, and if you have an exam coming up, I wish you all the very best. Go rock it. Have fun. Thank you very much for watching and have a lovely day ahead.